so we have two more things we want to share with you, and actually in between the two I will show you something else. The first one is the transformer, and the other one is the tool for the handling of thermal behavior of machine. And in between I will show you the user subroutine as it is right now. It's going to be just a demo, so it's not part of your printout, but I will show you a demo on the Groovy subroutine and how to apply it on something special. So let's talk about some transformer and what we can do with Flux in general. So of course there are different type of transformers: single phase, three phase, auto transformer, reactors, anything you want to say. So let's call it coils and transformer, or reactors and transformers. And we want to design or try to understand those machines. We need to evaluate losses, the efficiency, behavior, saturation, any type of things like this. Even we need to also protect them. And so the classical simulation test we're going to do is actually low load, short circuit, in restaurant, but we will also be able to do any power factor we are interested in, just by putting a load on the secondary and seeing how it works. In fact, you could actually take a transformer and you could bring it in the middle of Portunus instead of having the equivalent model of a transformer, just as the right transformer, and then see how you can maybe how it would behave if you have failure on the secondary side, and how it would reflect it to the primary side. So analyzing what kind of analysis we're going to do: iron losses, Trey losses, Joule losses, but also magnetizing reactance, and we're going to try to find the equivalent circuit parameters for the transformers. The other interesting thing is to do thermal or mechanical. Maybe some transformer, maybe the coil vibrates or things like this, or you're mechanically you're interested in seeing what's happening if a coil has a very strong force applied to it. And so those one, most of the time we do through third-party tools. Why? Well, it's because if we do the thermal of a transformer, usually, or not usually, but often you have oil-filled transformers, and so you will have convective motion inside the tank, and Flux doesn't know. It's not a CFD tool, it's only straight thermal. So for what Flux is concerned, if we were doing a thermal, we would probably stop just on the surface of all the components and just put convection or radiation coefficient to actually set the losses. Other tools are much better, Fluent, Star CCM, and other type like this. So that's why we would go through third-party physics, multi-physics tool. And if you remember, Vincent showed you this morning that for the next version, version 12, we will have these connections that exist. So we'll be able to extend to all of those things. For the vibration, you can already start using LMS Virtual Lab, as that is not limited to rotating motion type of tools. Here we have some references, and in fact we also have a reference in Taiwan, and we have one of the representatives of the company right here, Philippe Transformers. So the geometry, well, that's another big issue. Is that okay? For small, and by the way, I didn't talk about the power, but you can do from high power to low power, any type of transformer. We also do, I'll show you some things that goes for high frequency in a little later. But the geometry is not very easy all the time. So if you take just a small transformer, maybe it's just going to be a very basic type of geometry. But a big machine like this, well, most of the time you have a CAD system, and so this is how we're going to, we're not going to enter it directly, but we'll try to import it. And because it's going to be much easier. So, by the way, when you import, then you have other issues. Because there are a lot of things on this transformer, for example, that are here, maybe for mechanical reason, for connection reason or stuff like this that may not have an effect on the solution we want to do. The leads, sometimes you cannot ignore them because they may create a distortion in the field locally, but most of the time we'll try to ignore them. Here we have those big, we have those screws or whatever goes from one side to the other. Those one, well, I think sometimes we just are going to describe them as part of the material, like your regular materials, more than anything else. But there may be some corners, I'm not too sure, some funny things happening, and those ones we definitely don't want to import them because this is going to create us a very complicated geometry to mesh, but sometimes we cannot avoid to do it. But the other thing is we can do full or reduced model, and because most of the time we're going to work in 3D. And for example, this one is shown in 2D. But this is kind of a transformer. You can adjust the air gap. It's whatever you want to call it. It's more a reactor, power reactor, or something like this. It's shown in 2D, but actually this machine should more be in 3D because we will have, it's not so thick. And then where you have air gap or things like this, you will have some leakage, and this leakage is going to be fringing, fringing on the third dimension, and this fringing is going to be very, very important. And so in 2D we will not be able to capture it. But so very often we have to actually go 3D. Obviously, if we do something like this, you can see all the clamps on the side. You may have flitch plates and stuff like this. Those are not, you cannot show them in 2D. And we're going to look at losses inside there. 2D, that would not appear because we would cut it right in the middle and we would not have those very important features, okay? So it's going to be 3D, but then think about the number of elements you're going to have. And so as much as we can, we're going to try to work on the fraction of the machine. So here we just work on 1/4 of the transformers. We have, we can see the core, the primary and secondary, and then we have all the tanks that close the whole stuff. We're going to do the study inside steady state AC. So the difference between steady state and transient, sometimes we cannot go to transient. If we are very interested in harmonic effect or things like this, or saturation, if we want very, very, very accurate saturation, sometimes we have no choice but to go to transient magnetic. Steady state AC will assume that all the signal is sinusoidal. But if you really think about it, if you are in transient, in nonlinear, the flux density variation is not transient, it's not sinusoidal anymore, it's an ellipse. So it's not going to work so much. So we can do, it still works, because when we're trying to approximate energy or things like this, we'll be able to actually do a very good computation. But if we're looking at the local variation of the flux density through the cycle, then a very accurate description can only be taken in transient magnetic. So the test, again, short circuit, open circuit rated condition. As I said, it's for a single frequency. Sometimes you could actually work on harmonics by building more of the signal and working with the fact that you can set a saturation in a certain way in the transformer before you apply a higher harmonic, but it's not very recommended. So this one is going to be the full signal, really. And in fact, the one I'm going to show you, I need to do transient because the signal is not at all sinusoidal. And then steady state thermal, okay, for the thermal behavior. Remember, this is without any losses through fluid. It's just one that stopped at the border of the transformer, nothing else. So a little example of a transformer, courtesy of WTC. I don't remember what this stands for. Do you remember? No. It's a company actually in Australia. Yes. 150 MVA transformer, 132 kV, 14.1 kV. This is the flux model. So here we can see a few features there. The clamps, we have actually some other type of ferrures on the side
This is shunts maybe on the side to try to mitigate the flux leakage into the tank and try to limit the losses inside the tank. So those shunt would be there. We see here in this case, in this very particular case, we had actually some connections that were there also. Electric circuit is very easy. We have a primary where we have all the voltage sources, the primary coil, and then we have a secondary where we have the low voltage and all the load. Okay? So in this case, it's just a resistive load, no power factor or anything like this. So again, here we have the core, the shunt, they're all laminated. In this case, they will be non-conductive. They're part of volume region. If we look at it again, those are the shunt lamination, the green part in the middle. So all of this is laminated. So there will be only a mu, and I don't know why it says here it's a mu anyway. The tank frame, or it's the tank itself. What we're going to say is that the tank is small enough that we do not have to compute the eddy current inside. Well, that means that the thickness of the tank would be larger than the skin depth inside the tank, okay? Which for a magnetic material can actually be very easy to do. So we are going to use a different type of formulation. It means we're not going to mesh the volume, but we're only going to mix the surface, and we'll have a surface impedance formulation on the face. So there will be a mu and a resistivity. Then we have the clamps actually, thin sheet thickness, so SEM IP. Actually, those ones are very thin in this case, so their skin depth is smaller. The skin depth is larger than the thickness of the plate here, and so in this case we have another type of formulation. We can still put a face, and it's just a different formulation where we compute the distribution of the eddy current through the thickness, but from the face. And lots of other conductive parts, so solid conductor volume regions, conductive parts, so those would be actually maybe the connection in the back and things like this. And then winding bus bars, current sources, no eddy current, this is just a regular coil with a number of turns. I brought this here, something we can do. This comes a little in the middle, but I guess we talked about it this morning, so I will not go very far. The point here is that we can actually, it's laminated. So if we were going to do every lamination, it would not be possible to mesh and do anything. But what we can do is we can still take into account the fact that it's laminated. See here, this is laminated with an air gap. But instead of doing all of this, we'll take one single one, and then we are going to mesh all of this, and we'll apply a special type of material property, laminated properties, and the program is going to compute the mu, the permeability, cross-lamination, from the characteristic of the material, the thickness of the lamination, and the stacking factor. So the stacking factor will give actually information on the size of the air gap between the lamination. So that's actually applicable. It's applicable just in regular transformer sheet like this, but if for some reason you had a core which is laminated this way, why not, I don't know, you could also do it. So going back to the description of my material from before, we have non-mesh coils for the high voltage and low voltage. So that's a different type of coils we can have. We don't really care at this point. If we were interested in eddy current or proximity effect computation or eddy current in the coil, then we will have to actually mesh the whole coil. However, this is coming very soon actually. No, actually this is a mesh coil without any losses, so it doesn't really matter. But if we have with every losses, then we will have to do all of this to actually do the whole computation. Okay, here is the model of the transformer. And so now what we are interested in computing are all those impedances.
in different ways. So we'll see how we can actually look at those. And just give you the information about, so the primary magnetizing inductance, the secondary magnetizing inductance, the leakage on both sides, and of course the losses, that's just the regular losses of the stuff. Actually, this shows you something that it's this information is not on the real, on the same type of transformer. It's another one. I'll come back to this big transformer after. But let me just show you this because I think it's an interesting example. So this is a kind of a funky type of things. We have a core here. We can adjust the air gap in it because that is going to help me play on the inductance of the coil and things like this. We have a primary. The primary is made of those many turns here. And we have a secondary, which is a big sheet of aluminum. Okay, and here we have actually two phases, so we can get one or the other in this case. Let's see, if I look at the circuit, here is the circuit. So you can see every single turn of what I showed. So there is one first on the top, one series on the second, on the lower part of the secondary. Here is the secondary, which is also made of solid sheet, and on it we have actually a resistor. And then we have a voltage source. And in this case, what we're going to do is only power the top part of the circuit, and then we'll keep the secondary part as a closed loop. And we will see if there is crosstalk between the top and the bottom. So we have those resistors here only to measure the voltage of those things. If I look at it, this is the source, so I can actually look inside the physics, by the way. Look at the electric circuit, voltage source. Here we go. The voltage source is defined in a nice way here. It's using a trapezoidal periodical function. So it's basically giving the rise time, the constant part, the lower time, and then the constant part at the end. And it's periodical, so it means every time it finishes, it restarts. So here it's done, it's all prepared for variable frequency. I have a parameters which is called frequency somewhere, we'll look at it after. And so now we can see, so 1 over the frequency is actually the cycle, and it's actually giving you how much of the cycle it actually works with. And in fact, let's see this frequency parameters, here it is, it's in the I/O parameters. Here we have frequency, and this is 1 kilohertz. Okay, so if I plot the signals, this is what I get here. Okay, on the primary side. So let's look on the secondary side. So that's what I get on the. This is what happens. The current. It's actually the current that goes through the primary. Okay, so why is it like this? It's because you have all the inductance that slow down the rise of the current. Then you have the switching and it goes the other side. So that's curve number 2. Curve number 3, that's actually the current that goes inside. Ooh, wait a minute, let me just make sure I'm looking at the resistor. Yeah, in the resistor. So it's the current that goes through the secondary, actually. So it would be directly associated to the voltage, of course, because it's only current. And the fourth one here is actually, this is the, let's see, what do we have here? If I put them on top of each other, so this is the current through. We have the current through the voltage source. We have the current through the primary, which is opposite. It's just because we assume that the current is negative in the source, basically. And then this is what we find the current in the secondary. So what do we have here? We have, as I said before, everything here is solid. Okay. So now I can look at different things. Of course, this is a flux density distribution. Nothing special here. We can see it does actually go through, so we should actually see some crosstalk eventually here. We have some saturation on the side. It's not a very saturated type of things, it's not a very high current, so there is no question on the side. Another thing we would like to see is eventually the current density, and I think I'm actually probably going to have trouble here, but let's try to see. Here we go. We have the current, so this is the current density in one of the coils here. I can look at it in all of this stuff. So the current, it's a current density. It's a current density because it's not uniform because it's distributed. I have a solid conductor, and so we have a frequency here, and so at different time it's going to have a different value. So let's try to do this picture here with all of these primary coils. So I'm going to take current density. We'll just first do all the primary coil here first. So let's go primary. So it's going to be 1, 2. Well, I don't know where, so I'll just take all the primary. Here we go. No, not what I wanted. Go back to the top here. I should be able to select everything at once. Here we go. Okay. So here we have everything. So the problem is at the bottom I have almost nothing, so I'm going to just move my scale towards the top and see how it's distributed inside here. And now you can see it's not quite uniform. You have a distribution, but you can see it's actually distributed as you go. So let's see now the distribution inside those two here. So let's. I want to identify them because I don't want to put all of them at the same time. Let's look at the regions here, phase region, and it's going to be part of the secondary, and my guess is that it's 1 and 2. So we're going to do the same computation of those two. So here we go. Let's do a new plot here, new ISO values, and I'm going to go for here. And J is okay. And now it's giving me the distribution of the current in those also. So we have a higher distribution on the inside because this is where we have the core. We probably have a slightly lower flux on the outside, not as much compression. This is why you have this distribution. So that's another type of transformer. It's not the one you find on the regular power distribution line, but nevertheless, this is a type of tool that we can do. If we go higher frequency, we can also go to copper trace. Very often those things are in 3D. This one was actually axisymmetric because it's only one single core, but you could imagine to have having a three-phase transformer in this way. So let's go back to our problem here. And if you remember the transformer we did and everything, we're going to first do an open circuit condition. So it means we put a very high resistor here, so we'll have no current at all on the secondary. And what we'll have is basically the magnetizing current only on the primary. So out of there we'll do the magnetizing current. The core is going to be saturated, so that's going to be probably a good place to actually compute core losses. And, but the leakage, we won't have the leakage here. So here is a picture. So as we said, the core is indeed saturated, every single leg, the corner here, even part of the top. This gives you the arrows of the flux density, so you can see that's for one phase, okay? This is done in AC. Now we're going to look at one single phase, and we can look around through the stuff. So because we have that, we can get some Joule losses here on the tank. We'll see it's probably not the most important part. We'll have the losses of the tank in short circuit that are going to be much more important. The energy of the domain is going to give us the magnetizing reactance. And the iron losses that we have in this case, it's 416 joules. So out of there, this magnetic energy, we're going to actually compute the magnetizing reactance for each side. Now we're going to do the short circuit, and in the short circuit, we'll do a very small resistance here. So what's going to happen here? There will be almost no flux density distribution distribution inside the core because we are short circuit, and everything will be beside the two coils. So no magnetizing current in this case. The core is going to be non-saturated, low flux density, so forget about trying to compute any iron losses here. But on the other hand, we'll have large leakage flux, so we'll be able to get the leakage reactance, and we'll be able to compute the losses in the tank. Here is a short circuit, as you can see, nothing is here. We have, except of course in the middle of the core, but that's absolutely nothing. And then you can see the flux actually is not conducted anymore, but it actually goes all over the place. The losses, so the stray losses on the tank are actually almost 1.4 kilowatts. The energy of this domain here, 1024 joules, will give us the leakage reactance. Some other things we can get here, because this is where they are the most important, are the forces on the coil. Okay? And very important, because if the coils are not well aligned, it can actually throw the coils out of the place here. And then here we can, well, we'll have a heavy joule losses, of course, on the winding in short circuit, but that's going to be the short circuit case. It's not the radio case. So here are the information. We get the reactive power here, leakage reactance, the joule losses, eddy current losses, well, in the winding. So that's actually would be using a formula based on the radial magnetic induction that we would apply, and stray losses. Here we can see the losses inside the tank. So all those arrows show you the current distribution inside the tank. That's just to give you an idea of the current, the eddy current losses inside the winding. So this is actually going to be programmed inside the software also. So you're going to be able to get this kind of stuff. This is if I have basically a coil which is made of many turns. I have the height A, and we have the width B, and then we have a pitch between the coils. I can actually compute the eddy current losses from the radial and axial component of the flux. I'll let you go look at this formula. It's actually, you can find it in an IEEE paper from 1988. It's a very old formulation. The Laplace forces, so they will be computed by doing the J cross B on the coil. So if we have the volume on the coil, we can do an integral of J cross B on the coil. There are two parts to it. There is a DC component and a double frequency component that superimposed. Here you have the different information. Okay, that even gives you the orientation of those losses. Okay, not losses, forces. I'm sorry. Eventually, we can bring the thermal computation. So again, the thermal computation on the tank here, it's assuming that we are just doing convection losses on the inside and on the outside, okay? We don't have any oil going around, anything like this. What we put is we put the convection coefficient on the surface. That's all. Just an example here, you have a computation that's a full tank, a little different. It's a tank which has a little notches and stuff like this. Okay, I have a little more information here, so I'll go through this example. This is a transformer. It's a power transformer. I'm trying to remember where it's from. Well, I guess I don't have the information right here. It's one that was completely done here. It's from our colleagues in Brazil. It's a Siemens. I think it's a Siemens transformer, actually. So here we have the full tank here. There is a small air reactor on the side. We have the core, we have the clamps up and down. And really the issue here is, you see how the wall of the transformer goes here? We have a little problem here because we have stray losses that are right here, and they're hitting this wall in a dangerous way. So we need to find out how we're going to mitigate those losses. So here, that's just telling you how we computed all of those losses. And what we are going to do is analyze those shields. So let's go forward. We did the 3D time harmonic simulation, and then we actually did I do believe we have conducting, but this is actually with surface impedance and things like this. But let's actually go to the computation we've done. We've done one with no shielding, so no mitigation, so the initial case. We've done a computation with a shield, which is made of aluminum. And then we've done another computation with the shanks. So here, that's the first one with the shielding. Okay, that's, I believe, the aluminum shielding. And this is the one with the shanks, just to show you how it changes. The one with nothing, you saw it was before. So here is the externals, the circuit. This is the input part. This is the, so actually, yeah, this was even coupled to the air core reactor. I mean, there were quite a few things that were happening in this stuff. But let's go further. This is the mesh, and let's look at the result. So this is the case where there is no shield, nothing at all. And what we can see is that if we look at the leakage right there, we have tangential component of the flux right here. So it's probably absorbed by the wall, and it's going to bring us a lot of losses. Now here is the same one with aluminum. Now what they did is it actually pushed the field leakage a little further, but obviously the aluminum is taking, the shield in aluminum is taking the most of it. So we may have actually a lot of losses inside here. And then let's do the last one, and in this case we have the shunt, and look how the flux densities has actually gone down. And what's happening is that the flux is basically channeled by the shunt, and nothing goes to the tank. So now if we go look at the result, this is the eddy current losses when we have nothing to protect it. Then eddy current in the tank when we have the shielding. So you can see we don't see anything right there. We still have stuff on the side. And then this is the one with the shunt. And look, we have absolutely nothing here. We have a little higher parts right at the top here, but it's very, very localized and probably can be handled much better. And here is the picture at the end once it's all done. This is the case, let's see, this is the final case. So basically what it shows you is behind the shunt, which is right here, we only have 62 degrees. Up there it's behind the air core. And right there, which is right at the corner, if you see the geometry right there, right at the corner, this is where we have the most, and it's very localized. Right there, we have two places with 104 degree centigrade, but you can see that most of it is just in the vicinity of 60, 65 degrees. So it actually mitigates the problem quite well. I think because we're getting close, I'm not going to go much further. This was a case done on proximity effect computation. I'm actually going to skip this one. And let's move to the next thing. So before I do MotorCAD, I really want to show you the user subroutine and how it's applied to some motors. So we're going back to the motor at this point. So I'm going to just close this. Go back. I'm just going to close completely the program. And I'm going to go back here to, let's see, right there. And we're going to work on a switch reluctance machine. This one here. So the way the switch reluctance machine works is usually you have a very, very high voltage to try to bring the current very fast. And then the current is modulated so that you never exceed the maximum current. So here is the machine here. This is, let's see, what do we have? 8-6 phase. Okay, let's look at it from the beginning here, directly, when it was started. Okay. So what do we have here? We have the different, this is the lamination here. And then we have right there the current, so the winding. If I look at the circuit, here it is. And as I said, we want to modulate the current distribution. So we